You can hear me, right? Yes. Great. Okay, so this afternoon's session is on random forests and start decision trees. Before I begin, can I have just a quick show of hands as to who's used random forests before? Okay, and who thinks they, of those who said they use them, who knows how they work? Not a lot of confidence. Okay, great. So hopefully this, therefore, based on the fact that 90% of people didn't raise their hands, this shouldn't be too new, so we should cover some new and exciting things. What we're going to do is we're going to start with the kind of like fundamentals. So where random forests come from, that obviously involves starting with the decision tree. And we're going to go from the decision tree through a motivational example onto the random forest, how you basically create a random forest from decision trees. We'll then have a classification exercise, which I and Serby will be helping you with. And then we'll move on to the second part of the session, which will have another exercise to open it, which is a regression example. And then we're going to go on to some of like the practical applications of random forests, what things you can do to make them more usable, more interpretable, and how you kind of actually use them in practice. And I'll also go through, if we have time, an example of some research that we did using random forests. The one thing that is on there, which I thought to take off, is gradient boosting. Not going to have time, I don't think, so we'll skip that for today, and you can just ask me in my free time. Please don't. So, fundamentals. The name decision tree comes from its tree-like structure. So, the decision tree looks like a tree. It's got branches, it's got leaves, it's got a root bone. What they are is they are an algorithm or a representation of an algorithm that uses conditional statements only. So if we have a very, very simple tree, like the one on your right, if an animal's blue, then it's a lobster. If it's not blue, then it's a cat. Obviously, this isn't exhaustive, but just to give you an idea of how that splitting occurs. Okay. I'm actually now just going to launch straight into a wider example. I think that concept is hopefully straightforward, and show you how this works with a larger tree. And the example I'm going to go with is a summer example, because we're in the summer. More specifically, we're going to look at a scenario that might resemble JAWS, but totally isn't JAWS for copyright reasons. Fun little tidbit, the people who produced JAWS, Universal, didn't copyright the image, but they did copyright the name. So I can use that without attributing it or asking for permission, which is great. And you can too. Fun fact for the day. So, my example is whether or not people are going to be eaten by a shark at the beach. And we have a bunch of input variables, and these are whether or not they went swimming, whether or not the waters were full of sharks, whether or not they decided to impersonate a seal or a penguin, and finally, whether or not they wore a swimsuit made out of bacon. And we've got some just simple binary inputs and then a binary output. So, was that person eaten by a shark? Based on all that information, I can construct a tree that kind of represents all of those, a very extensive set of 8 points. And basically, if they didn't go swimming, then they weren't eaten by a shark. Like, in no cases did someone who didn't go swimming, in no cases was someone who didn't go swimming eaten by a shark. So we kind of split there, and that first basically separates out a good chunk of information. And then we kind of go down that right fork of the tree, where they're wearing bacon swimwear. Yes, then they were eaten by a shark. No. Whether water shark infested. No, then they weren't eaten by a shark. Yes. Well, then finally, did they impersonate a seal? Okay. How we actually arrive at that structure, which is the most efficient structure for this decision tree, is to basically look at the split that gives us effectively the lowest impurity. Right? And what I mean by impurity is by that which minimizes the amount of incorrect examples on either side of the split. Okay. Now there are a few methods to doing this. Entropy is one. The one that we're going to look at, and one that's quite commonly used, is G impurity. Okay, and I will explain this in detail now. So, if I take that first question, did they or did they not go swimming? If they didn't go swimming, then they weren't attacked by a shark. And there are no yes examples on the left side of that split. Okay, so the impurity there is 0. On the other side, we've got some impurity. So you can see that some people who did go swimming were attacked, and some people who didn't go swimming weren't attacked. Okay. If we look at all the others, you can kind of see that there's impurity on both sides. So hopefully you're kind of looking at this and going, okay, well, I think I can understand why that first question is the right one to start with, because it does split the impurity, or have the impurity just on one side, and we have a pure split on the other side. Okay. Now, in terms of how we actually go about calculating the Gini impurity, I'm not going to go. I don't have too many equations because I want to keep it kind of intuitive. I don't want to just bombard you with them because that's not fun for anyone. But we basically take the probability of the output that we're looking for, so that's yes, and then times it by 1 minus probability, and we do that across all classes. Okay, and you can see how this arrives at 0. Okay, because we have 0 times 1 minus 0. So we basically calculate that for all of the leaves. Okay, and then we essentially average it across each of those branches. Okay, and that gives us the Gini impurity for the top left of 0.3, and then you can see that the others are higher, right? And the Gini impurity ranges between 0 and 0.5. So you want to be as close to 0 as possible, and you want to be as far away from 0.5 as possible. Okay, everyone okay with that? Great. Once we've got our first decision point identified, we then basically build up from there. Okay, so on this side we have no impurity, so that's basically fixed. We don't need to do anything on that side, and then we just repeat the process on this right side. Okay, and we calculate new Gini impurities and average them again, and then find the next split. Okay, so a single decision tree, as you've probably seen, is quite easy to kind of follow through and interpret how it's making these decisions. We can actually just pull it out directly from the tree and put it into a sentence, plain language, quite easily. In this case, if you go swimming and either wear swimwear made out of bacon or impersonate a seal or penguin in shark-infested waters, then we're going to be eaten by a shark. I say probably there because for the data scientists among you, you're probably going, well, this isn't a very big data set. That's only 8 people. Okay, so that's a decision tree. When we move from a decision tree to a random forest, we basically just create lots of decision trees. Okay? And we take our series of decision trees and we look at all of their individual outputs and we average them, and that gives us our final result. Okay? It's commonly called consensus. The question, however, is, I've just shown you with a data set how you arrive at a decision tree. We're thinking, well, if I give it the same data set, each decision tree is going to be the same. Yeah? And you would be right if you're thinking that. So we need to basically have a way of creating different trees from the same data set. Okay. And as I've said at the bottom, monocultures are bad. So what we need to do is we need to create diversity within our random forest. So we have trees that are outputting different results. And the way we do that is by something called bootstrap aggregating or bagging. Okay. Who here's had the term bagging before? Yeah, a few of you comfortable with bagging? Those who have raised their hands? No? Okay. So we're going to do it again to like low equations. As I said, what we need to do is we need to create different trees. And what we do is we basically look at our full training set and we take examples from the training set with replacements to create subsamples, like subsets. Okay. And we use each of those to train the tree. It's kind of graphically illustrated on the right here. But what you've probably noticed is that you can end up with the same example pairing within that sample that you use to train that individual tree. Okay, so that's the with replacement there. And this enables you to kind of build up different trees. Yeah. and that's how we end up with our random forest. Yeah.
The images, I kind of get the decision trees.
Yeah.
Is it deliberate there's 3 prongs coming out the first one?
They're just illustrative.
There's no meaning.
No, there's no meaning. It's just I've just changed the colours so you can see that the tree's different. You can have a decision tree where it does have more than 2 branches. Yeah, this is just purely this one. Okay, so one decision tree is quite easy to follow through. When we have lots of trees, they're all going to have their individual conditional paths through the tree. With the examples that you're going to look at in a second, we're not going to be using too many trees, but it's quite common to use random forests with hundreds of trees. Probably not going to have thousands of trees, but hundreds is quite common. And in that case, you're not going to be looking at the decision path for each tree. Okay, so they start to lose their interpretability. So we've gone from something that's quite intuitive, quite easy to interpret, to something that isn't. So I've made my facile comment at the bottom. Turns out we can't simply trees to the forest. So what you're going to do now is we're going to get stuck into the first classification exercise. This is the going to be using the Palmer penguin dataset. There's a penguin theme here, along with the sharks. We're going to look at the 4 features that are included there, which is body mass, bill length, bill depth, and flip length. You're then going to just kind of do some exploratory data analysis. So look at pairwise combinations of the variables, which I will touch on again later. So I'm going to do that specifically. You're going to fit a random forest classifier to the data. And initially, I just want you to use kind of pairs of variables as the input using a relatively small number of trees, maximum depth of 2. And the reason we're doing that is because we've got a tree explainer in the exercise. So you'll actually be able to work your going to trace the path through the decision tree and see how it's outputting each different penguin species. You're going to calculate its accuracy, and then we're going to hopefully draw some conclusions from that, and then move on to looking at all 4 variables, varying the number of trees, maximum depth, and just repeat that process. It's quite a small data set, so it should run on your laptops very quickly. And yeah, we're going to just have a look at decision boundary there. So if you go to the Slack, you'll find, I think I posted it an hour and a half ago. You should find the GitHub repo for this towards the bottom. If you want to get started with that, Serby and I will basically be going around if any of you have questions. Yeah.
Oh, sorry, what do you mean by replacement? And you were talking about taking subsets of data with replacement.
Yeah, so if you've got like a bag of, let's say we've got green and orange balls, okay, and you're trying to work out, probabilities of picking one from the bag. If you take a green ball out, you have 2 options, right? You either keep it out, and that obviously reduces the number in the bag, and you can't take that same green ball, or you could put it back and have the same probability of drawing that green ball as before. Okay, so that's with replacement. Okay, and the reason why we ensure that we have replacement is because this is obviously probabilistic, the way that we're kind of pulling them randomly. It gives you greater variation in the sample, like in the subsamples that you use to train each decision tree. Yeah, thank you.
Can you just unpack why we did? Because we had a data set that is the data we observed. We've got a single tree in general. So why do we want to create a random forest? What advantage?
Yeah, so basically it enables you to build up like a more non-linear, flexible algorithm that can approximate a wider range of functions. Is the answer, right? It's kind of analogous to going for like bigger depth and width in a neural network. So if we add more trees which have been trained differently and they're deeper and wider, then we get a greater representation of possible functions that fit the data. Right? And the data that we're quite often using is never really as simple as the example that I showed, which obviously is very easy to split. Quite often we're throwing random forests at more complex problems, where a single decision tree just isn't necessarily going to be able to capture everything that's going on. Does that answer your question? Any other questions before we get started with the exercise?
So what's the main difference between the bootstrap and bagging?
So bootstrap and aggregating, bagging is basically taking those two terms and forming a sort of portmanteau. Yeah, portmanteau. So it's, aggregating is the bootstrapping is basically taking samples with replacement. So it's the bootstrapping, so creating sub samples of new, well, not new data, but creating new samples from the data, which we're using to train each tree separately. Okay, so that's the bootstrapping. The aggregating is basically just bringing it together. Okay. If anyone does get stuck, it should be, I think, bug free. But if anyone spots a bug or gets stuck, just raise your hand and I'll come over. Okay. Hopefully everyone's had a play with random forests and kind of had them working out probability, or not probability, working out and predicting whether or not a penguin belongs to a particular species. We've had some people saying, "Oh, you know, my trees are starting to overfit," and this is what I'm going to touch on now. Well, actually, first I'm going to talk about feature engineering to a certain extent. Hopefully, in your sort of like exploratory data analysis, you realise that some pairs of variables gave like a really clear split between all three species and others didn't. If you did train your random forest just on the pairwise inputs, you would see that this one, which is looking at bill length and bill depth, is quite accurate, you know, like 6%. And then if you're looking at flip length and body mass, it's less than 80. Okay, and that's obviously because the data between the chin strap and the Adley penguins, it's not separable in that input space. Okay, and the random forest can't do that for you. It's not magic. Okay, so it can't create some magic decision boundary if it doesn't have the data to underpin it. Okay, so that's point one. And then on to the overfitting. This is very few trees with low depth. I've got to put the numbers on. No, I didn't. I think this was 6 trees with a depth of 2. This was about 8 trees with a depth of 4, and this was 10 trees with a depth of 12. What you can see happening is that this is obviously not a great decision boundary, it's really coarse. This one's pretty good. And as we move over to this one, it's basically trying to fit almost like individual data points, right? It's got too much flexibility, so it starts overfitting. It creates a decision boundary that kind of wraps around individual data points, okay? And that's obviously not what we want, right? This would generalize quite poorly. And again, it's kind of analogous to with your artificial neural networks, which you looked at earlier in the week, having too much depth, too much width, and training for too long. Okay, everyone happy with that? Great. Any questions before we move on to the second exercise?
Any sort of guidance between number of trees and depth of decisions?
It's kind of trial and error, really. If you were to try and work out what it is yourself, if you've got very complex data and lots of input variables, then obviously you're going to need more depth and more trees to do so. Starting with sort of like 100 trees and a depth of 32, it's probably going to get you some of the way there as like starting point, and then you can either use techniques like the grid search or Bayesian optimization to optimize the number of trees and the maximum depth as model hyperparameters. So you've got the standard grab bag of tricks that you can use with other models to explore which hyperparameter combinations are better for your problem. Okay. To answer your question, it's a bit of a non-answer. But...
And then some sort of trade-off between those two hyperparameters, the depth and the...
Yeah, I mean, although you've probably noticed that these train really rapidly on your laptop, and they do, even when you've got, I've got a model, which I'm going to talk about in a bit, where I've got 100,000 examples going in, and I was looking at a maximum depth of 50 and 200 trees, and it still trains in a minute or two. So it's very rapid. Obviously, if I want to explore lots of different combinations, then it starts to slow down. Right. especially because I threw, and another thing which I'm going to talk about is platt scaling. I threw that one as well. And then when you're running a random forest with platt scaling, don't worry, I will explain platt scaling. Then it's, I was looking at 5 days to go through all those permutations. Okay, so it can take time. Okay, so part 2 is kind of, as I said, going to focus more on some practical aspects and usability of random forests. We're actually going to start with a regression exercise, and that is for a reason that should hopefully become quite apparent. So you're going to dive back into your laptops, and what we're going to do is we're going to explore a very hard problem, the cubic polynomial, and you're going to again start with a fairly small random forest with low depth and a low number of trees, and you're going to create predictions for that cubic function using the random forest. Now we're starting with a low number of trees because I kind of want you to see how, as you add more trees and more depth, it gets closer to the function. Okay, so each time that you retrain it with new hyperparameter settings, we're obviously going to take a look at the function and see how it evolves. And we basically want to be, and again, this will train very rapidly. And we want to increase the number of trees, and then go back, and then increase the number of depth, and go back, and then start to increase them at the same time. Okay, and kind of comment on the patterns that appear. And that's point 6. And then we're going to move on to a larger in the X domain test set. Okay, and we're just going to see what that does, and again make some commentary and plot it and see what it's doing when what its behavior is outside of the training set. Okay, everyone happy with that? Great. Again, Serby and I will be on hand to answer questions. Okay, so has everyone had like a play with the Russian random forest and had a go at looking at its performance outside of the training set? Yeah, some people nodding. Show of hands who made it to 0.9. Okay, about half people in the room. So the reason why I start points 8 and 9 is because if you have a random forest which is doing incredibly well on your training set and on your validation set and on a test set which is within the limits of your training set, fantastic. But as soon as you start to move outside, its performance basically drops off, right? And it's probably worse than useless. And the reason for this is, well, when we talked about what random forests are doing, and they're basically using conditional statements, then when you're down at the very bottom layer, it's going to have values like if x is less than or less than 1, then do this, right? If x is 1 is the lowest x value you have in my training set, it's not going to know what to do at x is 0 or x equals -1. So I haven't given that information, so it can't create the branching that's required to fit the function around that part of the X domain. Okay, so an ordinary random forest, which hopefully you should have seen whilst you've been playing with it, cannot extrapolate. Okay, so they're great if your training data is representative of the real world problem or anything in situ, and you're not going to be expecting extreme events that are going to pop out of nowhere that aren't in your training set. Okay, does that make sense? Yeah, cool. So I'm going to talk a little bit about some practical things, as I said before, and how we can actually make random forests more useful, or how we can start to interpret them in different ways. And the thing that I'm going to start with first is platt scaling, which I mentioned a couple of minutes ago. So when we have a classification class, what a random forest does is it has a whole bunch of trees that are essentially given 1 vote. Okay, and if we have two choices that we're trying to predict, and 8 trees say it's choice A and 2 trees say it's choice B, then we get choice A. Okay, we don't really have any way of understanding what the uncertainty is around that prediction. And this is where flat scaling comes into effect, right? And it actually was designed not for random forests. It was originally designed for support vector machines. And there we go, final point. And the reason why it was kind of developed there is because people were looking at decision boundaries that support vector machines were creating, and they were just assigning uncertainty based on distance from the decision boundary, which is probably not a great way to do things, especially because it assumes a certain kind of probability distribution, which may not actually be the underlying probability distribution in real life. Okay. So platt scaling basically couples a logistic regression layer to the end of your random forest. And what we do is, there we go. If we're looking at the probability that y equals our positive class, so we've got a binary classification problem, given some input variables, it is just the equation for logistic regression, and we've got our prediction using the random forest in there, okay, instead of x. Okay, it's really that simple, and it gives us enables us to look at probability thresholds and the likelihood that our model is predicting a certain class. You know, we can basically say I'm going to set a threshold of 50%. If it's over 50% certain that the class is 1, so the positive class, I'm going to set as 1. Where you can kind of lower thresholds, look at what's going on at lower thresholds, and kind of see how your model's actually how its uncertainty is being created almost. That makes sense, right? So that's what platt scaling does. It basically gives us a way to capture uncertainty with a non-probabilistic model. So it takes a random forest and makes it, in a way, probabilistic. Okay.
What's the exponential term for?
So this is a sigmoid function. Yeah. I missed a couple of sessions this week. Was the logistic regression covered in any of them? I think it was. No. So what we do with logistic regression is we have this S-shaped function, okay, and that basically gives us our probability that it's 0, our probability that it's 1, and kind of the slope of that function, which is controlled by the parameters alpha and beta, kind of tells us how certain you are about that decision boundary. Okay, so if you end up with a decision boundary that's almost vertical, sorry, not a decision boundary, the shape of the sigma curve being almost vertical, then we're very, very certain about that's where a decision boundary being. That makes sense. Yes. Okay, so I'm going to move on to some techniques for exploring the interpretability of random forests. The first one is an ablation study. Is anyone familiar with ablation studies? No. One hand. So what it does is, if you imagine we have 5 input variables, we basically delete the input variable and train the model without it. And we basically do that for all 5 input variables, and you know why that animation is lagging. And we see what the change in our accuracy is. Okay, and that kind of gives us some understanding of how useful that individual variable is on its own to the predictive capability of the model. Okay, kind of useful. Yeah.
That a feature, or is that one of your samples?
That's a feature. Okay, so if we've got with our penguins, bill length, bill depth, flipper length, and body mass, if we just delete body mass and see how good our model is, and then we'll do it again for each of the other 3 variables. Okay, so if you have n variables, you're going to create n different models. Each one without, the ith model is going to lose the ith feature. Yeah. So yeah, that's kind of useful. Doesn't really tell us much about how effective that variable is in combination with other variables. So not perfect. Another technique that we can look at is feature permutation. And if you imagine that we have a whole bunch of data points, so each data point is a column, and same as with the previous slide, the variable is a row, we're just going to take one variable and we're going to shuffle it. Okay, so we're going to swap the values for that variable around with other data points within our training set. Okay, sorry, within the validation set. So you typically do it with the validation data. Now, obviously, that's going to screw up the results, right? Because if we're trying to predict, again, looking at the penguin and which was the heaviest penguin? Was it the Adelaide penguin? I can't remember. Who's still looking at the penguin data? Someone tell me. But if we kind of like swap those values around, then obviously we're going to suddenly say that Adelaide penguin, if that is the heaviest one, has a lightweight, and that's going to throw the predictions out. Okay, so we can kind of see in a similar way to the ablation study how much each variable, when we jumble it around, how much it's throwing out the predictions, and therefore have an idea of how important it is for the model's ability to make predictions. And you basically make as many shuffles as you want, and you do that for every single feature. Okay, and then we just aggregate the loss of performance across each shuffle within that feature. Okay, so if we've got k shuffles and then features, we're going to do k times n each permutations. Everyone happy with that? Yeah.
Well, already. Like temperature and
Yeah, so the bog standard feature permutation, that's a similar weakness for the ablation study, because you might have certain variables that are representing a lot of the same information. So if they're very strongly correlated, you could rip out, like, let's take the climate example. So either you have just salinity, or if we had, wind speeds from two different pressure levels, and we deleted one of them, and the model's predictions were still great. It's because we've still got a lot of the same information represented in that other wind speed at the higher or lower pressure level. Okay, so that's a limitation of your bog standard feature permutation. What you could do is you could start to remove combinations of variables. That's effective. Or you could start to look at Shapley values. Okay, so this kind of, when I said I was going to talk about your pairwise combinations and how you went from that and then to full variables, that's kind of what we're doing in a way with Shapley values. We basically take the power set of all of the input variables. Okay, so I'm not going to use the penguins. I'm going to use a slightly simpler example. Let's say I've got two input variables. I'd obviously have no input variables. I'd have input variable A as a model, input variable B as a model, and input variables A and B together as a model. Okay, and you basically want to explore all of those simultaneously, because then you can find out, when we cover this in time in more detail in a second, what each variable is adding onto the other models with and without it. Yeah. The problem with it, though, with doing that is that for those of you who are familiar with power sets in set theory, and for those of you who aren't, we have 2 to the n possible permutations. Okay, so if you have 10 input variables, you're looking at 2048 different permutations. Okay, which is too many to explore. Yeah. So in practice, we don't do that. We basically use an approximation. Okay, I'm not going to go into that because I'm starting to run short on time, but I will kind of illustrate it in more detail, going back to our "are you going to be eaten by a shark" example. So if we wanted to know how important whether or not you decide to dress up like a penguin and go swimming, whether that's going to get you eaten by a shark, we basically look at all of the models where we've added the penguin. Okay, so that would be the null set plus penguin. That would be wearing bacon swimwear plus penguin. That would be wearing bacon swimwear and swimming in shark infested waters plus penguin. Okay, and we look at the contribution that having the penguin, also impersonating a penguin, is adding on top of the prior model. Yeah, and what we do is we look at the total number of edges within that kind of graph, and we use that to create weights. Okay, so you can see that there are 4 different things that we can add into the null set, and penguins are obviously one of them. That's the only one in that row. So there are 4 edges, so the weight there will be 1/4. Okay, And we basically do that throughout the tree. The weights should sum up to 1. And so you can see that we've got 1/4 plus 3/12 plus 3/12 plus 1/4. So that checks. And we apply those weights to the marginal contributions we've identified from adding that variable, what it did to the predictive, to the prediction, as opposed to not having it. Is that clear? Probably a bit of a word soup.
So you said they added. Obviously, 3 of them on each one. So the first one's only 1. So yeah, I was adding 1/4, 12, 12. And
Yeah, sorry.
yes, there's 3 of them in that. Right?
Yeah. And that's basically what Shapley values are. They identify what the marginal contribution is of a feature on top of all other models that do and don't have that feature. Now, obviously, go back to your point, Mara, there are going to be some within that power set that have temperature and some that don't. And we're examining what salinity does when you add it to the ones with temperature and the ones that don't have temperature. So we get a better idea of how much contribution salinity is making on its own, irrespective of the shared information with temperature. Happy? So I'm going to finish the last 5 minutes with me talking, and then I'll ask more questions and then shut up. With an example of where I've applied random forests in the wild. So this kind of goes again back to something I got you to look at, which is that if you have data that isn't separable within some input space, then random forests or any other machine learning model aren't going to fix it. Okay, and there's a theory that wet bulb temperature is a really good predictor of whether or not a heat wave is going to be lethal. And we actually look at all of the heat waves, well, not all, but a good chunk of the heat waves that we have on record, and whether or not they're lethal or not. Wet bulb temperature cannot be used to separate the data. And people have tried random forests, they've tried sport vector machines, and they've tried neural networks to build classifiers using wet bulb temperature, and none of them work because the data isn't separable. Okay, so there's a piece missing. And what we realized is that, contrary to popular opinion, most people who pass away in heat waves, it's not actually due to something exotic like hypothermia. It's quite often down to just a good old-fashioned heart attack. And what's kind of going on under the hood is that when it starts to get hot, your blood vessels dilate. Okay, now this is accompanied with a drop in blood pressure, so your heart has to start working harder to keep the flow velocity in your arteries up. And this kind of kicks into action before sweating because this is your thermoregulatory first line of defense. Okay, and there is actually, you can kind of see there's like an evolutionary reason as to why this might be the case. Water's precious, it's scarce, but you don't want to lose water. You want to do whatever you can before you start losing water. Okay, and electrolytes, which again is something that you want, because if you sweat, then you need to replace the water with electrolytes. So if you can lose heat through other means first, you do. And that's what your body does, like that. So we realized that this was the problem, and we realized that actually, when we looked at a lot of the autopsy data, which is a really great read if you want something light before bed, that a lot of people who are dying in heat waves, they have underlying comorbidities. They have certain vulnerabilities, both just to some kind of sudden stress that's added to their heart, but also just in general on their cardiovascular system. So that can be age, or it can be obesity, or it can be combination, or something else. Okay, so we looked at that. We looked at people's physiological vulnerability and their adaptability, and tried to think about how we could encode people's ability to not just adjust to previous climate, but adjust to new climates and over all timeframes, and just threw all that into the model, right? And then we treated random forests like they were magic. The data that we had was very imbalanced. So it was about 99% were non-lethal heat waves. So that presented another challenge. We did look at various other sampling techniques, but what we went with in the end was something called synthetic minority over sampling technique. And this is basically where you look at your minority class, you look at a certain number of neighbors. So it could be 3 nearest neighbors, and you create a new data point that's similar to it. Okay, and this is useful because if you have quite high dimensionality to your problem, it kind of starts to help you overcome the curse of dimensionality. If we just had, I think in the end we had 15 input variables and just 1,000 data points. synthetic data generation techniques enable us to end up with about 100,000. So it kind of spans the space of it. This is the ground truth, okay, from the test set. So these bubbles represent, I know the numbers are probably not too clear, especially if you're in the back, but these represent the numbers of heat waves that were either lethal or non-lethal, with the non-lethal ones being blue and the lethal ones being red. Intuitive like that. And the size of the bubble obviously represents the number, and that's across Europe and Asia. Just so you know, the small bubble at the top is 70, and it's 110 for the non-lethal ones, but it's so it's imbalanced for a lot of non-lethal, but for lethal it ranges from 1 to 3. Okay. That's the error from using a wet bulb temperature classifier, right? So it's missing things left, right, and center. It's saying it's saying huge numbers of things that are non-lethal or lethal, and it's saying that lots of things that are lethal aren't. The problem you may be thinking, well, the bottom case is more problematic, but it's actually just as problematic for the first case, because if you cry wolf, people do stop listening. Right? There's a really interesting stat from America that shows when there's an earthquake or a hurricane, people go and buy insurance immediately after the event, and then they let it lapse, and then they get hit by one again, and they go out and buy it again, right? Because the warnings need to keep it doesn't stick if the events aren't happening. And that's our error. Our model's about 20 times better than the wet bulb temperature classifier. And we actually even took wet bulb temperature out as an input variable entirely, and we're just looking at the rates of change, which have, again, coming back to Lara's point, have very little information on the absolute conditions, because we have, they use the reference point, which we've stripped away. And the population vulnerability, and we ended up with almost the same things. Okay. So we think we're on the money with this. And this just shows it. So the F1 score, which is your metric of choice for imbalanced data problems, was 0.06 for the wet bulb temperature, which is bad. 0 is the worst it can be, and 1 is the best. For our model, it was 0.6. Is that plus 20? I meant 10. And when we remove wet bulb temperature and just have our other variables, then it's almost as good as with wet bulb temperature. So I think that this is the correct way to think about the lethality of humans. And we did also use backscaling and feature permutation and Shapley values and kind of looked at all that as well. But I'm not going to go through that. So final thoughts. Random forests are very easy to deploy. You can do a couple of lines of code from scikit-learn. They're quick to train as well. And they're very flexible. You can use them for lots of different problems. They, much like other machine learning algorithms, you need to do a bit of tuning to make sure that they don't overfit or that they don't underfit. And you do that primarily by looking under the trees and the maximum depth of those trees. They do suffer from some interpretability issues, especially if you've got hundreds of them. But we've covered some things, a whole bunch of techniques that we can use for exploring that. And very finally, doesn't matter what Shapley values say or feature permutation says, all you're getting with those is how the model arrives at its decision, right? It doesn't explain causality. Okay, and that's the same for every machine learning model. Couple of other final thoughts. They don't extrapolate. So use with caution if you're planning on using them to extrapolate. And then they do very well with imbalanced data problems. So we actually ran the random forest without synthetic minority oversampling technique, and the predictions were still pretty good. We just made them a bit better. Cool. I think that's it. If anyone has any other questions, feel free to ask. If not, a couple of minutes early, we can go and have more tea.